Okay, so this again continues with quiz 0. PF6-1, phosphorus with 6 fluorine atoms bound to it, and it's a polyatomic species. It's an anion, has a -1 charge. So first things first, we draw the Lewis dot structure. And this is going to be the same problem where after the Lewis dot structure, we'll look at the electronic geometry, molecular geometry, and so forth. Phosphorus has 5 valence electrons. Fluorine has 7, but there are 6 of them. Right, so that's going to be 42 electrons. This is an anion, -1 charge. Therefore, we have 1 additional electron. So, charge. Okay, so we're adding an electron. So this is going to give us a total of 48 electrons to work with. All right. Now, our phosphorus is the central atom, and it's surrounded by 6 fluorines. Now, one of the things, typically, not always, typically, when you have an atom surrounded by 6 other atoms, it is going to be octahedral geometry. But before we can get there, we're going to draw the Lewis dot structure. The reason I mention that is because the way I draw the Lewis dot structure will be coincident with octahedral geometry. The way to think about this is imagine the phosphorus is at the origin of an XYZ coordinate system. So we'll have a fluorine, fluorine, and I'll put 1 here and 1 there. Now, it doesn't matter. I mean, if you would have put all the fluorines on this side, you could still get the Lewis dot structure. It would just look really weird. Now what we need to do is we need to put in a single bond between each the phosphorus and each of the fluorine atoms. Fluorine looks weird. Okay, so 2, 4, 6, 8, 10, 12. So we've used 12 electrons. So we have 36 electrons to work with. As I'm doing this, closer. As I'm doing this, the first red flag that should have popped up as you listen to me say 2, 4, 6, 2, 4, 6, 8, 10, 12, there's 6 chemical bonds. Well, octet is 4 chemical bonds, 8 electrons at most. So we violated the octet rule. We have more than an octet. This is often referred to as an expanded octet. The reason I was taught that way, and that's how I've always referred to it, but if you think about it, 9 is not an expanded 8. Right? In other words, it's just 9, right? But we refer to anything greater than the octet as expanded. And again, this really, like I said, this is really a symptom that our Lewis dot structures are fundamentally incomplete in the theory. All right. So, with all that aside, phosphorus is violating the octet rule, and it can. And again, this I don't think I mentioned this in any of the videos earlier. Elements that have n equals 3 on the periodic table or greater can violate the octet rule. And the reason why is with more than 8 electrons. And the reason why is they have d orbitals. There are some other special cases, specifically with hydrogen, where you see some bonding that you don't expect with hydrogen, and it has nothing to do with p orbitals or d orbitals. But we'll get to that. So now we have 36 electrons. We're going to put them in as lone pairs. And we're going to see, I'm not going to count it out, we're going to see each fluorine is going to get 3 lone pairs, 6 electrons, and that's going to equal 36. You can count along at home. And that's 36. So we've used all of our electrons. As I mentioned, phosphorus is not obeying the octet rule, but that's fine. Fluorine actually is obeying the octet rule. So pick any one of these fluorines, 2, 4, 6, 8. So that's perfectly fine. Now what we need to think about is formal charge. First of all, should this molecule have a formal charge? And the answer is yes, of course it should. How do I know that? It's an anion. Look at, it's a polyatomic anion. It has a -1 charge. The only way that can happen, well, it's got to have a non-zero formal charge, a -1. Sometimes you can have 2 charges and they cancel out or partially cancel out. So you have to be careful about that. But I know at the end of the day, this molecule is going to have an overall -1 charge. Something about formal charge that might seem odd is like, why are we getting formal charges? Well, think of it this way. Imagine you had PF6 and it was neutral. What would your electron count be? Right? Well, if you go back here, your electron count would be your electron count would be 47. If you put in 47 electrons here, it's not going to work. And the reason it's not going to work is one of your fluorines is not going to have 3 lone pairs. It's going to have 2 lone pairs and then a radical. And you can't have a double bond or anything like that. You'd have an odd species anyway. So what we find is that the molecule will gain or lose electrons to satisfy the octet rule. So the octet rule is really what is driving formal charges, not the other way around. So with that said, let's calculate our formal charges. Some colors. Fluorine, and this will be true for all 6 of them, fluorine starts with 7 valence electrons, 2, 4, 6, 7, and therefore it has 0 formal charge. So it's not contributing, and it should be obvious, but we're going to do the math, because again, you don't want to skip steps. Phosphorus has 5 valence electrons. Well, look how many it has in this molecule. 1, 2, 3, 4, 5, 6. The formal way to calculate that is it has 12 electrons that are in bonding pairs, and you take 1/2 of it. The easiest way to do it is literally just to count the bonds like I did, and it's basically the same thing. But if you see, the reason I mention that is in a textbook, they'll give you the very formalized mathematical way of calculating that, which of course is correct, but it's tedious and it can be confusing. If you don't know what it means, you'll struggle with it. But again, using our Lewis-Dot structures in a graphical way really makes this kind of thing easier. So 5 valence electrons minus 6, so we have -1. And that is, of course, consistent because the entire anion, the entire molecule, is a polyatomic anion, so it has to have that -1. What about molecular geometry and molecular geometry, electronic geometry and molecular? In this case, they're both the same. We don't have a lone pair on the phosphorus, so the electronic geometry and molecular geometry are identical. 6 coordinate is octahedral geometry. which is abbreviated OH. And this will be true, again, for the electronic geometry and molecular geometry. I will do some examples where there's a lone pair on the central atom, and that distorts the geometry. This, of course, is something that from Vesper, from general chemistry, should ring a bell. In fact, also in Chemistry 112, another way to kind of get this to click in your mind of why it's significant, think about Chemistry 112, intermolecular forces. Well, what was one of the things that drove intermolecular forces? Is the molecule polar or is it nonpolar? And many times the presence of a lone pair will make the molecule polar. Not always, if you have two of them, for example, or there's some kind of symmetry going on. In this case, the molecule doesn't have any lone pairs, so again, our geometry is octahedral. What about orbital hybridization, right? Well, we have sp3, if we have 4 coordinate, right, like methane, can you have sp4, sp5? No. And hopefully you looked at me very odd when I said that, but it's something I've seen before, and if you don't understand what's going on, you have an s orbital, px, py, pz. sp3, that's the end of the game for the s and p orbitals. So what do you have to do? You have to get d orbitals. sp3 gets me tetrahedral 4-coordinate geometry. But what do I need to do to go beyond that, to trigonal bipyramidal or octahedral? Now I have to grab the d orbitals. And in this case, because it's octahedral, it will be sp3d2. All right? So that is our orbital hybridization. Orbital hybridization is right at the edge of chemical bonding before we get to molecular orbital theory. So the valence bond theory is a very good setup to get us to the next level, which is molecular orbital theory. And we'll be talking about that. But the reason I harp on that is because I want you to review valence bond theory, and I'll have some videos and talk about it briefly in class, because inherently in valence bond theory, you start looking at atomic orbitals as waves and how they combine as waves. In other words, an s orbital has positive phase, p orbitals have the lobes, positive and negative phase, and you have to have positive to positive phase and so forth. That's not in Lewis dot structures. If you think about it, there's no mechanism in any of that framework of Lewis dot structures for s and p orbitals and phase and so forth. That's where valence bond theory takes us. And that's what this is referring to. Then we go beyond that, and that's going to be, again, first week of classes with molecular orbital theory. So again, I just want to keep putting that seed in your mind of what you need to be thinking about. Is this polar or non-polar? Right? It's octahedral, so that means the molecule has symmetry if all the atoms are the same, or if you have a situation where you have, let's say this was bromine and this was bromine, the molecule would still have symmetry to it. And that's something we're going to get into in Chapter 2, by the way, in much greater detail. So, PF6 is octahedral, it's symmetrical, therefore there are 0 dipole moments. There's a term from Chemistry 111 that you should, net dipole moments, I should say, and therefore it's going to be nonpolar. Non-polar. Depending on who your professor was, they might describe it differently. The way I describe how to determine about is the molecule going to be polar or not is, imagine it's a game of tug of war. So you got the phosphorus in the center this fluorine is more electronegative than phosphorus, so it's pulling on the phosphorus. But this one that's exactly 180 degrees from it is also pulling on the phosphorus with the same magnitude. If it makes you feel better, put a little dash in here, and then you could turn these into vectors. And so it's vector addition. So they cancel out. So let's say that's the z-axis. So those two atoms cancel out. And then say this is the y-axis. Well, we got this fluorine and this fluorine. They're pulling in opposite directions. They cancel as well. And then we have the x-axis, same thing, cancel. And since all of the dipoles cancel, it's nonpolar. If I were to replace one of these fluorines with, say, a bromine or an iodine or a chlorine, that would still make the molecule octahedral, but I would have broken the symmetry. And in other words, this and this would not cancel, and therefore it would be polar. All right, so that's something in chapter 2. We're going to go into great discussion about that. So in Chemistry 111, 112, you didn't look at those type of geometries in most molecules. Maybe a few examples, but here we're going to find, especially with octahedral geometry, we can have lots of different combinations. But just to wrap this up, for PF6 minus 1, because it's octahedral, it's symmetrical, it's nonpolar. All the dipoles cancel out.